While we set up our second talk in this plenary session, it's a great pleasure to announce the second talk. It's given by Franco Nori from Riken in Japan. He provides us with a title saying Parity-Time Symmetric Optics, Extraordinary Momentum and Spin in Evanescent Waves, and the Quantum Spin Hall Effect of Light.
Too many pointers here. Thanks for coming here. I'll start first with the quantum spin Hall effect of light, and afterwards about PT symmetry in optics. This is the work done in collaboration with Konstantin Bliok and Daria Smirnova. And then I'll start first with a brief introduction of the electron part before going into the part for light. So here we have for all quantum Hall effects, the electrons flow through these edges, these lossless edge channels, with the rest of the system being insulating. And in the standard quantum Hall effect, the spin up or down, they go in the same direction. In the quantum spin Hall effect, spin up or down, they go in opposite direction. So therefore, we have the following, that there is this electron unidirectional edge channels, which is called the charge momentum lock-in. And in the quantum spin Hall effect, there is also unidirectional edge spin transport, but the edge stay with opposite spins propagating opposite directions. So this is different between the spin Hall effect and the normal quantum Hall effect. These topological states with spin momentum lock-in gave rise to new class of materials which are very trendy now, called topological insulators. Indeed, I'll be talking essentially about the optical analog of topological insulators. So this is quantum spin Hall effect and topological insulators for electrons first, before we go into the optical analog. This means the presence of these edge states at the interface between two-dimensional insulators. These modes are characterized by this strong spin momentum lock-in, where these opposite spins, blue and red, propagate in opposite directions. Some people call spin-filtered edge states or helical edge states in momentum space, but they're all essentially like this. There are some of the reviews are down there. So in this case, you can actually connect the valence and the conduction bands of the two insulators at the edge. This is the edge band structure for the up spins and the down spins, corresponding to these counter-propagating edge states. And there are more information down here. Now, there is a three-dimensional analog, which is a 3D generalization of the state we saw before. These insulators exhibit 2D surface modes, which are these helical massless fermions with the spin momentum lock-in, also known as vortex spin texture here. So you get this 3D. So we're going to look at these analogs for light of this. So far we talk about electrons, now we're going to switch more to photons. Photonic counterparts of electron Hall effects with unidirectional edge propagation have been reported in this magneto-optical system with broken T symmetry, but these are not needed because the photons themselves are relativistic spin-1 particles that they naturally exhibit intrinsic spin-orbit interaction effects, including Berry phase and some properties coming from Maxwell equations, these angular momentum properties. So the missing part in the above optical effects is the quantum spin Hall effect for photons. So let's look at this right now. The surface modes with spin momentum lock-in. This is the key ingredient to have this effect here. So there are some proposals, some topological photonic insulators created in complex metamaterials. What we're focusing instead is on free space light. Already possesses intrinsic quantum spin Hall effect, and that simple natural materials, such as metals, that have the surface plasmon polarity modes, they exhibit some features that resemble topological insulators. Of course, they're very different, but there are strong analogies. And we show that there are the transverse spin in evanescent waves. We have been working on this for some time. And the spin control unidirectional excitation of surface modes or waveguide modes can be interpreted as manifestations of the quantum spin Hall effect of light. So this is a brief review of the basic angular momentum properties of light. So the bulk modes of free light that is propagating plane waves. So this is the helicity, and the photons carry this intrinsic angular momentum or spin, which is this one here. And this corresponds to this has the longitudinal helicity dependent spin. So therefore it propagates along Z, and the spin or angular momentum is longitudinal and depends on sigma, the helicity. So this is what they call the helicopter mode. So therefore you propagate in this direction here, and the Z-axis moves like this. This would be the helicopter mode. But if you have a metal and you have the vacuum here, there is here evanescent waves. There is exponential decay, which corresponds to a K, which is imaginary. And that gives rise to this exponential decay. So instead of having your typical helicopter mode, you get what some people call the John Travolta mode. Probably the older people in the audience who saw Saturday Night Live remember this. So therefore, in this case, there is the propagation of the electric field is on the XZ plane. They form this cycloid. So therefore, there is a cycloid that goes in this direction as opposed to the one on the XY plane. So therefore, the evanescent modes, they do have spin because you get this K has this decay exponentially on X, corresponds to this imaginary one, and this gives rise to this transverse helicity independent spin. And this is weird because the angular momentum is supposed to be longitudinal, not transverse, and helicity dependent. We have been working on this for several years. There are several papers discussing this. So the S, which is supposed to be longitudinal, appears to be transverse in this case. And this comes from this transversality condition. And then this component produces this XZ plane rotation of the electromagnetic fields and generates this unusual transverse spin in evanescent waves. There is a classical analog of it. So even though the wave is propagating from here to there, the actual particles are moving in this way. So therefore, when the particles move in this direction here, the angular momentum is directed in this direction here, even though the wave is propagating along the Z-axis. Of course, this is a surface effect. Once you go into the bulk, it's not going to happen. It only happens near the edge. It's an edge mode. So this brings back to this extraordinary momentum and spin on evanescent waves. There is a very long paper here, and there's additional work done before here. So this is standard textbook statements. The momentum of light is determined by the Poynting vector. This is well known. The momentum of light is directed along the wave vector and is independent of polarization. Everybody knows this in textbooks. The spin angular momentum of light is determined by the circular polarization and is directed along the wave vector. This is standard textbook material. What we have found is that several statements that you find in textbooks can be violated when you look carefully at these edge states. And there are other statements which were proven to be actually incorrect in other series of papers, which I will not discuss today. This is an experiment done by the group in Bristol looking at direct measurements of this extraordinary optical momentum and transverse spin-dependent force using a nanocantilever. So the light is coming here, circularly polarized, is bouncing, boing here. and there is this, the canonical momentum, the standard one, in this direction, given the standard radiation pressure, and there is this weak spin force coming this spin momentum in field theory is called Berifante, but there it was considered to be like a virtual kind of thing. We have found this actually is real, and we have found ways to actually measure it. There are different lasers with different helicities being applied to this cantilever, and it's possible to measure the actual canonical momentum plus the perpendicular one, this spin of momentum. The canonical one is small, it's piconewtons. The transverse one is even smaller, but the measurements and the theory correspond pretty well, and it's nicely understood, this one here. There are other experiments, which I will not describe here. So therefore, this transverse spin survives in TE-TM surface modes. Most important, opposite direction of propagation correspond to opposite transverse spins, which is the quantum spin Hall effect of light. So this is the schematic diagram here for these counter-propagating modes with the momentum which is oriented either in this direction here or in the opposite direction here, even though the standard propagation is along the z-axis. The metal vacuum interface resembles, using a condensed matter analogy, the interface between a semi-metal and the insulator. But instead of having an insulator, we have a metal. Because if you're a photon, the metal is your insulator below the plasma frequency. And here, instead of having a topological insulator, we have the vacuum. So the Dirac cone is coming for free. And the surface mode are the surface plasmon polaritons. So therefore, there is a, even though the systems are brutally different, one of them is fermions, another one is bosons, another one has massless, another one has mass, they are very, very different. There are significant analogies to these very different systems. You can also look at momentum space. Here you can see these helical massless excitations. And then, so therefore, looking at the surface plasma polaritons, you can, the usual metals exhibit the surface modes with spin momentum locking as in 3D topological insulators. So this is essentially like almost like an optical analog of 3D topological insulators. Now, this has been observed in many different experiments, some of them looking at surface plasma polaritons, and other ones looking at waveguide modes in photonic crystals. And these modes exhibit this spin momentum locking, which are typical for 3D topological insulators. So there are several experimental groups independently reported experiments on a variety of different systems looking at spin-dependent unidirectional excitations. The typical configuration is this one here. There's a transversely incident light, and then there's a scatterer, which is this one here, coupling to surface modes, and then there is a spin-dependent direction of surface modes, which is controlled by the helicity. So the blue one pushes here, and the red one pushes in the opposite direction. This is one example here, 2014, by the group of Arno, Rajan and company. They're looking at, they realize a chiral waveguide coupler where the handness of the incident light determines the propagation direction in the waveguide, and these to control and manipulate light in optical waveguides and for new design in optical sensors. There is this group by Kuipers and company looking at the helicity coupled to the left or right hand rightwards propagating modes with near unity directionality. And their measurements demonstrate the possibility of coupling the spin to a photonic pathway. There's another paper here looking at this way to control the propagation direction, exactly where more than 90% of the optical power is launched into one direction or the other one. And these supposed to be implications for quantum nanophotonics. And so these are some of the diagrams here where the helicity on the left or the right can send the light propagating either on the right or the left. Here there is a photonic crystal waveguide where you can actually control the helicity and get the photons propagating left or right. There are cases here with Zayats and company and Rodriguez Fortunio on spin orbit coupling surface plasmon. Again, the direction of propagation of the surface plasma waves, which intrinsically has this unusual transverse spin, determine the scattering direction for spin-carrying photons. And this is the case where you can have this left polarized or right one. You can generate the surface plasma polarity waves in one direction or another one. So let me get a conclusion of this part before we go into the other part, which is the topological, the parity-time symmetric. We have shown that pure free space light already possesses intrinsic quantum spin Hall effect, and that simple natural materials such as metals supporting these surface plasma polarity modes exhibit features that resemble 3D topological insulators. There are quite a few experiments actually that can be explained like this using these ideas that we have been developing for some time, and that light possesses this intrinsic quantum spin Hall effect, which means strong spin momentum locking surface Maxwell modes. And then this is different from the origin of the quantum spin Hall effect for electrons, because these are fermions, and this is spin momentum coupling rather than spinor momentum coupling, and there are many differences which I will not describe here. I will just go into the second talk here, which is this one here, and then it goes here. Oh, this one here. Okay, there are different routes for novel structure with new functionalities, including photonic crystals and metamaterials. Are there any other routes for structure which have properties which are not attainable in natural existing materials? And one possibility is to play with gain and loss. So you have the coupling, which is one knob. Another knob is the gain. Another one is the loss. By playing with these three knobs, you can actually generate new devices, new functionalities. But these are not constrained to only photonics. Could be for acoustics, for mechanics, for optomechanics, electronics, plasmonics, for a variety of different systems. Well, this could be in principle used for optical circulators, isolators, routers. Now, how to describe this? If the system conserves energy, then you need to have a Hamiltonian system. But if the system is open and is dissipative, then you can use non-Hermitian Hamiltonian, a non-Hermitian system. If it is Hermitian, the eigenvalues are real. Otherwise, it will be, if you have complex eigenvalues, then that corresponds to non-Hermitian Hamiltonian. But is it possible, starting from a non-Hermitian Hamiltonian, to produce real eigenvalues? See some people sitting in the back. There might be some seats in the front. And the answer is yes. You can, if you had the Hamiltonian commuting with the PT operator, then you can get a real eigenvalues, even though the starting point is non-Hermitian, which you need to describe a dissipated system. If you don't have this condition, you go back to the complex eigenvalue case. So therefore, these parity-time symmetric Hamiltonians that satisfy this condition can have an entirely real eigenvalue spectrum. So this is a brief summary here. The parity space P operator changes P and X, and the time reversal operator operates in this manner here. If you operate P twice or T twice, you get the identity, and they commute with each other, and the PT operator is this one here. So this is a summary from quantum mechanics in one page. There is a cartoon or manga, a way to describe this. You have two systems here. You can exchange them. So that's your parity operator. Or you can do time reversal symmetry, where the gain becomes loss, loss becomes gain. This should be dark blue, but somehow I messed it up. This can be seen if you have, let's say, a ton of money in the stock market and you lose it. If you could reverse time, the loss becomes a gain. Of course, it's not going to happen, but if you could do it. So you can apply P operator first, and then you can apply T, reverse it, or apply both of them at the same time. Now, if you have a Schrödinger equation, which are the conditions to be PT symmetric, where you get T to minus T, X to minus X, complex conjugate, etc., etc. And when you do this, if the wave function satisfies the Schrodinger equation, so does this PT operator on this, provided that this condition is met. So this is your condition to have this PT symmetry. But that's for the Schrodinger equation. If you have an electric field in a Whispery gallery modes, then you need to describe it using this para-axial equation of diffraction for the electric field. And they are mathematically equivalent. There is a way to map the classical problem and the quantum problem together, and PT symmetric means that this condition on the Schrodinger equation maps on this condition the para-axial equation of diffraction here. So we're going to be focusing on this case here, but importing some results that were developed initially for PT symmetric Hamiltonians here. But this will be our focus here. Now, you can couple structures that have this balance gain and loss. You can couple these whispering gallery modes, 2 or 3, so one of them will be lossy, another one has gain. You can couple waveguides. There are different possible configurations here. So let's look at one example here. So this is optical diode or non-reciprocal light transmission. So the light is coming here on these fiber optics. Here is coupled via evanescent wave coupling. So the light is moving here on the blue donut. We're talking about donuts. Then we have the red donut here, and then it's flying here in this direction here. But it doesn't do it in the opposite direction. It's a diode. Light propagates in one direction, but not the opposite. So therefore, these are the whispering gallery modes resonators trap light efficiently via total internal reflection at the rim of this convex shape made from a dielectric material such as silica. When two identical optical resonators couple, they form this photonic molecule. And the individual modes undergo a mode splitting, similar to what happened with electronic levels when you form molecules from atoms. So in this case, you can get the light coming in one direction. So here is coupled in here, and then evanescent coupled there, and then here. But if you try to do in the opposite direction, so the light comes here, evanescent wave coupling here, and then evanescent wave coupling right there, is not going to come out. So this is a nonlinear optical isolator based on parity-time symmetry. This is a pair of coupled microtoroid resonators, one providing gain, another one loss. When you have this nonlinearity present, the light passes in one direction, but not in the opposite direction. And then in this case, when you have balanced regions containing equal amounts of loss and gain, you talk about PT symmetry. The whole thing is balancing out. And this is a combination of parity, spatial parity, and time reversal symmetry. And then there is a spontaneous symmetry breaking. The mode with unbroken PT symmetry are distributed evenly among the red and the blue. But the PT broken modes tend to spontaneously concentrate the energy in one of them. So you essentially break the symmetry. And this is a summary of an experiment. This was done with Sahin, Ozdemir, and Lang Yang at the University of Washington University, St. Louis. And then this is a PT symmetry microresonator. This is the top view. There is a gap there, and this is the edge microtoroids. The microtoroids are put at the edge of two samples, and you can put them close to each other and further apart. So you need to be able to control the coupling between them. And the coupling is done by putting them closer to each other or further apart. So there is a gap here where you can see, and there is here this fiber optics on the left to the right, so there is here this evanescent wave coupling here, there, and comes out there. So when the coupling strength is increased, so that means they're put together closer to each other, and then what happens? If there is no gain or loss, one of them has gain because one of them has is doped with erbium. So the erbium doped one has gain, the other one has loss, but before you dope them, when you couple them together, the frequencies, if their two resonators are equal, their frequencies are omega naught. When you couple them together, they split. So you get this red and red one. But once you get this gain and loss compensating with each other, then you don't get this red split. You get this blue one. Nothing is happening until the coupling becomes large enough. At that point, there is a phase transition. There is this bifurcation there happening. This is the real part, and this is the imaginary part. So in this case, both of them are lossy. They are both of them losing energy. In one case, it's erbium doped. There is gain, there is loss, but eventually they just merge near zero. It's a bit lossy. So there is a phase transition. It's a spontaneous PT symmetry breaking. In the broken symmetry phase, the eigenvalues become complex. Okay, the background I already described, and then this is summary here. So here, this is summary here. In the broken phase, gain saturation, there is gain saturation and enhanced nonlinearity. So in this case, the transmission is saturates. But remember that here, this is in microwatts. This laser pointer is about milliwatts. So therefore, the light involved here is about 3 orders of magnitude weaker than the one I'm holding here with my hand. So this happens at very low power. So there is this nonlinearity-induced non-reciprocal light transmission in the broken PT symmetry phase. So in this case, the light goes back and forth equally. In this case, it's not. And the significance is that the light transmission is resonantly enhanced in one direction, but completely prevented in the other direction. And then, so this is an example here. So the input-output relations become nonlinear in the broken PT phase. This is one here where there is a saturation of about few microwatts. So the field localizes effectively in one of the whispering Galler modes, enhancing nonlinearity. So the field is localized in the resonator with gain, regardless of whether the field is input on the lossy or the other one. So in this case, there is a reciprocal transmission, the linear regime. So in this case, there is unbroken, broken symmetry. It doesn't matter if you go forward or backwards, the results are pretty much the same. But in the nonlinear regime, there is a reciprocal transmission. If you go backward and forward, in the forward regime, in the broken symmetry, is completely obliterated. And without a pump, there is no signal. You need to pump it to be able to actually get the signal there. So the signal is obliterated to zero. Before, we had one resonator was lossy and the other one had gain. Now, let's put both resonators are passive, namely both are lossy. So we talked about the optical diode. Oh, this is Sahin and Langyan, and this is the winning by losing. So we're going to talk about number 2 here. There will be no time for talking about this. We have many results, but these are just 2 examples here. Okay, no, I'm pushing the wrong button here. Okay, so we talked about these optical diodes. We also look at how to do electromagnetically induced transparency and outlet town splitting with the systems. Now we're going to talk about lacing, where you have 2 resonators here, and then you induce additional loss by putting a micro tip here. So the electric field moves from this toroid to this one here, in producing lacing. So you're actually increasing loss in the system, and even though you're increasing the loss, you actually produce lacing, called winning by losing. Reversing the effects of loss by adding more loss. This doesn't happen in investments. So you have two couple resonators are here. You put a nanotip here, and when you put the nanotip, the loss increases, and you can get the lacing here. And these effects are caused by the non-Hermitian nature of the system. Okay, this is, okay, let me see here. So, okay, here we're going to experimentally probe the system in the vicinity of this exceptional point. Exceptional point means when the real imaginary part of the systems, they merge, of the eigenvalues. You need to have 2 independent parameters, 2 knobs, which are, in this will be the coupling strength and the loss added by the tip. By tuning these 2 parameters, allow the system to approach this exceptional point. And then the physics that follows from these non-Hermitian properties show several counterintuitive features, especially near the so-called exceptional points in parameter space, where the two complex eigenvalues coalesce in both the real and imaginary parts. So now this is the cartoon of the system. There are here these two fibers. You put them on fire, you stretch them in. There is evanescent wave coupling. And this is the top view. There is a gap here. And the tip here is a bit hard to see, but if you magnify here, the tip is this one here. And the tip is affecting one of the resonators. So initially the system is here. When you increase the loss, then the real imaginary parts, they merge into this point here. This is the exceptional point where both eigenmodes merge. So when you're increasing the loss, they behave symmetrically. But beyond this point, what happens? One of them loses energy very quickly and is dumping energy into the other one. So even though collectively you're increasing the amount of loss, the loss is being distributed in a non-even manner within the system. So one of them is losing energy much faster by dumping into the other one. So therefore here the real parts supermode coalesce. One of the modes become more lossy, the other one less lossy. And there is a symmetry breaking after the exceptional point. At the beginning is symmetric, and then symmetry breaking. And then, okay, let me look at this one. So at the beginning, when you increase the loss, lacing first stops, and then it grows. So therefore, increasing the loss pushes the system close to the exceptional point, localizes the field in the less lossy resonator. Beyond this point, increasing the loss helps to recover Raman lacing. So here, I'll be finishing soon. So so these exceptional points are these non-Hermitian degeneracy points where both the complex eigenvalues and eigenfunctions of these dissipated systems coalesce. The presence of these exceptional points affects the system very drastically. There is resonant trapping, singular topology, mode exchange, many things happening, which I haven't described. But then a couple optical system can be brought to this vicinity of the exceptional point by steering the coupling strength or the loss difference of the constituents. And this is the first demonstration of this exceptional point in coupled passive resonators. And then you control it by the distance between them and the coupling. And the eigenvalues coalesce in the real parts and bifurcate eventually. One of the modes becomes more lossy while the other offset less lossy. There is symmetry break in exceptional point. And then you can get this revival of lacing. And the significance is that you can actually reverse the effects of loss by introducing even more loss. And lacing is recovered despite of this increase in loss, in stark contrast to what would be expected from conventional laser theory. And thanks for your attention.
Franco, thank you very much for this interesting talk. And before I even request it, here's a question.
Thank you. So, no, the first part of your talk was really an eye-opener for me. And when you were talking about spin momentum locking. There's a very simple system, which is a metamaterial with a planar chiral design. Such system has eigenstates, which are elliptically polarized. And elliptically polarized in one direction, clockwise, in opposite direction, anti-clockwise. In your terminology, I believe this is the simplest system which has spin momentum locking. And it is known from 2003 and has been extensively studied by us and other people in years to come. Would you qualify this as a system showing spin momentum locking?
Well, I will have to study those papers there because what we have found theoretically has been elements of this has been seen on different experiments occurring on photonic waveguides, in surface plasma polaritons, but they were never put together in a cohesive, unified manner.
I fully
so
agree.
If you have more examples, I'll be very glad to talk to you afterwards.
We will share examples. Thank you very much. I agree with you.
But I'm very interested on hearing from you more examples because we're writing a review on this, trying to connect these different experiments and different theories together.
Excellent. There's another question over there. Please.
Yeah, I have a question on the quantum spin-Hall effect analogy on surface plasma polaritons, and you have shown some excellent examples of separate the propagation directions depending on the circular polarization of incident light on a metallic plane. Then we're actually there are way more examples of separating light on the surface plasmons. Depending on the circular polarizations. Then my question is, are they all explained by quantum spin-Hall effect, or there are some particular structures or examples which can be explained by quantum spin-Hall effect, and there are some others which cannot?
Yeah, it's a good point. I did show only 4 examples, but I agree with you, there are many more, and I didn't show them because of time limitations. And then the ones we have looked at, they can be understood. We have found similarities between all these experiments and 3D topological insulators. There are other ones you're describing, I will have to sit down and see each one of them to see where are the analogies, where the analogies end, where they stop, which are the differences. But we have so far, of the order of 10, I showed 4, there are many more. But I'm not saying that this is an exhaustive list. It's only, I show a few examples, but certainly there are more.
Okay,
We
thank
could
you.
discuss afterwards.
One final question over there, please, and then we...
So you have shown resonators, one with gain, one with loss, 2 with loss, and what happens when you have 2 with gain? Is there anything interesting?
Sorry, will you please repeat?
When you have 2 resonators with gain, what happens?
Okay, we have been looking mostly, we need to have gain and loss to do PT symmetry. If they are both lossy or both of them with gain, you're not going to have this balance. So in order to get the balance, you need to have one with gain and the other one with loss. In fact, what you see here, the diagram here, it's in order to get this behavior, which is no response, and then the phase transition, you need to have one with gain and loss. If they're both of them with gain or both of them with loss, it's not going to happen. If you have, in this case, they're both lossy, nothing happened. One with gain, one with loss, eventually they semi-compensate, and then they get this behavior. But you don't get the PT symmetry with both of them with gain.
Okay, in the interest of time, and I'm always sad to quench an interesting discussion, please also let's thank our speaker again. Thank you very much.